This video will cover section 1.5, Analyzing Graphs of Functions. We are going to learn how to use the vertical line test to check if a graph is the graph of a function. We're going to find the zeros of functions, and we're going to determine intervals on which functions are increasing or decreasing, and determine the relative maximum and relative minimum values of functions. Then we're going to determine the average rate of change of a function, which we'll be using the same formula as the slope. And we will be identifying even and odd functions. So let's get started. We have the graph of a function, and we already know that what makes the line the graph of the function, and in this case it's called f, is that collection of ordered pairs. So each pair, as you could see here, instead of saying x comma y, we're using function notation where we're saying that the f of x, the output, is the same as y. And so the collection of all of those points, once we put them together, they form the line, the solid line. So it's made out of points. And those points have to be in the domain of x. Well, the x value needs to be part of the domain of x. So as we have already mentioned in previous sections, x is the directed distance from the y-axis. In other words, x is the horizontal distance. And the y value, or the f of x, which is outputs, both of them, is the directed distance from the x-axis. But I like to refer to it as the vertical distance. But you could see that it will be the distance from here to here, for example. So each point will have the horizontal distance and the vertical distance. Now the collection of all those points, it forms the graph. So to identify the domain, which is what we're going to do here on example 1, we are going to consider all the x values that are within the function. And so we have here domain. So it's going to be the number that will correspond here will be -1. We know for sure because we have a -1 there. And we have every single number between -1 and 0. So I don't want you to think that the only x values will be -1, 0, 1, 2, 3, 4, and 5 without including it. I want you to imagine the whole number line. So all the fractions that go from -1 to 0. Also all the fractions that go from 0 to 1, like 1/2, 1/3, 2/9, all of those. And then 1, and then all the fractions from 1 to 2, like 1 1/2 or 3/2 or 7/6, all of those fractions. And then we keep going, and we will stop there. Now you could see that we have a full circle, a closed circle. That's what we call it because it is color in it. So if it was a hole, it will be closed. So that means that we include the number -1. But on the other side, for the number 5, we have an open circle. It's not filled in. So if it was a hole, it will be an open hole. So that means that the number 5 for x is not included. And so the interval, it means that we have everything in between, every single decimal Every single number that will not be an integer will also be part of the domain. So it will be extremely wrong if we were to just list them like this, like just the integers. Wrong, don't do that. The domain needs to be given in an interval, and it will be from -1. We always start from small to large, to +5, but 5 is not included. So you have to make sure you use parentheses there. If we had to give our answer as a set or as an inequality, it will be all the x values that are greater, I'm sorry, not greater, but less, no, yes, greater or equal to -1. And we say equal because the -1 is included. You could see it on the circle, and we also use the square bracket. And then less than 5. And we do not include 5, so we don't need the equal part on the inequality symbol. Okay, so that is for domain. Now let's talk about the range. So for the range, we're going to consider the smallest y value that we have, and it is going to be included, and that number I believe will be -3. Oh, we could also see it here. And then the largest y value that we see here is going to be at 3. It's also a point. And even if you didn't have a point, the simple fact of having a solid line, that will mean that the y value will be included. So that is +3. So for the range, and of course, don't forget that everything in between those numbers will also be included. So in this case, the range will be square bracket from -3 to +3 square bracket. Let's see what else. Well, we did the domain, which was the x values, and for that we use from -1 to 5, but without including 5 because of the open circle. Now for part B, well, let's write this one before we move on. Let's write it as a set. So it could be something like any x such that, oh, and not x, but y, because we're talking about range. Such that y is greater than or equal to -3 and less than or equal to +3. Okay, now we're going to answer the question for part B, and it says find the function values. So what's happening here is that we are given the x value of -1, and we need to find the y value that corresponds to it. So we have to locate -1 on the graph for x, which is here, and the point that corresponds to the y value that corresponds to that graph will be the +1, the one that is here, the one that is on the actual graph. And that will be +1 for the y value. Now for the next question, they're saying if x is equal to 2, what is the y value? So at x equals 2 is here, we have to trace the graph, or imagine you're drawing a line, and until you touch the graph, that will be the point that you are looking for. So when x is equal to 2, this was the point, when x is 2, the y value is -3. So that will be the answer to that question. And I just noticed that I made a mistake here. Instead of using parentheses, I should use the set notation. This is the way that you would write it as an inequality, and then if you want to write it as a set for the domain, it will just be with the curly bracket and then x such that, that's what the vertical line means, x is greater than or equal to -1 and is less than 5. And then we close with curly brackets again. And this type of notation again is called interval. And what we're saying is that all the numbers in between the integers are also included. So let's move on to the next question. And this is probably the easiest thing we will do in this class. It's called the vertical line test. And it is a test that it is intended to verify if the graph represents the graph of a function. So if you recall, we said something about the x values. For a relation to be a function, we said something about the x values cannot repeat. And so if we have a graph, and let's say that you have something like that, if we trace a vertical line, we're only touching 1 point, so that will be okay. But if we have a graph that, for example, a circle, that is the graph of an equation, if we trace a vertical line, then we are touching 2 points. So that will be not a function. And so that's the purpose of the vertical line test. Let's do another example. So if we have vertical line, for example, like the ones with the equation, let's pretend this is a number 3. So the equation will be x equals 3. We covered those in a previous section. And so if we use the vertical line test to test if this is a function, it's going to be a big no. How many points are we touching here? Well, definitely more than 1 point. And in fact, we're touching infinitely many. All the points on the line are the ones that we're touching. And lines or graphs, curves, the graphs of equations, they are made at, if they're solid, it's because they're made out of the accumulation of points. So in this case, we say definitely not a function. But as a quick review of one of the methods that we learned to identify if a function is a function, if the graph, well, how can I say this? If a set of points will represent a function. So for example, if I take 2 points from here, let's say I could take 3, 2. And then if I take a point here, it could be 3, -2. So remember, one of the conditions for us to have a function was that the x value only had one partner. It was only related to one unique y value. And in this case, 3 is being related to 2 and also to -2. So definitely not a function. In the case of the circle here, I'm just going to make up some numbers. So we could set -1, I don't know, 4. And then we could say -1, -4. So in this case, definitely you could see again that the x value is repeating and is related to 2 different y values. So that's why it's also not a function. So moving on, and just to before we move on, the definition says a set of points in a coordinate plane is the graph of y as a function of x. Here, y is the dependent, x is the dependent. No, I'm sorry, I'll just write it down. X is the independent or the input. and y is the dependent variable or the output. So if we have that, if y will be a function of x if and only if no vertical line intersects the graph at more than one point. So the only one that passed the vertical line test, because it was only intersected at one point, was my first example. Okay, next topic, zeros of a function. So here the word zero, it refers to the x values for which f of x equals 0. In other words, the x values for which y is equal to 0. So because the y value or the output is equal to 0, then because of that, we call them zeros. But they're actually x values. Those x values could be numbers other than 0. They could be negative numbers. They could be irrational numbers. They could be integers, positive integers. They could be even 0. But all of these are x values. And if their y value that corresponds to it happens to be 0, then we consider them the zeros of the function. Now, based on that, with all these examples that I wrote here, I'm going to write them as in order pairs. So it will be like negative 10 comma 0. I could have negative, no, it was actually positive. Square root of 2 comma 0. And then here I will have 3 comma 0. And then here I will have 0 comma 0. So remember, we call them the zeros of the function because the y value is equal to 0. So if you were to visualize these points, they will be located along the x-axis. The x-axis. And so because of that, we could also refer to them as x-intercepts. All of those. So we're going to learn how to find them, how to identify them, how to use them to our advantage. And then we're going to learn a lot of things on how to go from, for example, I'm just going to write this a little nicer. For example, if we were given the x-intercepts, we're going to learn how to find the zeros. That's the word of the day, zeros, such as what I had here. And what was this? X equals 3. And then we had x equals 0. So they will be the zeros. Sometimes we will refer to them as the roots of the equation. And then we're going to look at different types of zeros, especially in chapter 2. So right now, just think about the x values for which the y value is 0. And if those numbers are real, here in chapter 1, they're all real. In chapter 2, we will introduce imaginary numbers. But for now, if those numbers are real, the zeros, which are the x values, then they will be x-intercepts. So right here, we're going to find the zeros of the function and pretend you don't have the graph. And pretend the graph doesn't have the answer. So one of the ways for us to find zeros of a function, remember the word zeros, it's related to the x-intercept. So x-intercepts are those points for which the opposite letter, in this case y, is equal to 0. So we're finding the x values that will go there, for which the y will be 0. So the logical step to find an x-intercept is to let y equal to 0, right? So y is the same as f of x. It represents the output. So because of that, we're going to get this f of x and turn it into a 0. Then I'm going to just rewrite the equation. And one thing I can do to find the zeros is I could try to factor the quadratic function. So the only way I can get 3x squared from multiplying two factors will be by multiplying 3x times x. Then I have a negative sign here, which means that I have my possibilities for the signs that will go here and here could be one of each, a positive and a negative. So I don't know where they go, so I'm just going to try to put them there. And now for number 10, I have some factors. So I'm going to find the factors of 10, actually of negative 10. So those will be 1 and 10, or 2 and 5. And I'm gonna have to choose a number to be positive and one negative because we want the factors of negative 10. So let's just assume that we're gonna have the negative here, and this will be positive. This will be negative, and this will be positive. So let's try to place them here. So I'm gonna go with I don't even know. Let's try 10 here and negative 1. How do we check if it works? Well, we have to multiply 3x times negative 1 is negative 3x. And then we have to multiply 10, positive 10 times x, 10x. So if we combine like terms, we will get positive 7x. So that's definitely wrong. So what can I do now? Well, I can change the signs. And so I can put the negative here and the positive here. So let's see if this works. Positive 3x times positive 1 is positive 3x. Negative 10 times x is negative 10x. So combine like terms, negative 7x definitely does not work because what I'm trying to get is positive 1x. So what I'm going to do now is change the order of the numbers. And, oh, okay, I just realized something. Okay, so let's place the 10 here and the 1 here. And so if I do that, it will be 3x times 1. That will be 3x. And then 10 times, negative 10 times x is negative 10x. I feel like I already did this one. Yes, it was the other way. Anyways, it seems like I will not be able to factor it. And I'll tell you how I know that. Well, because I looked at the graph and we have here a 5/3. I mean, I think I should be able to factor it. Let's not give up. Actually, I just thought of something. Okay. So 3x, x, and let's go with the other combination, the one that had 5 and 2. So let's do that. Now, what we're going to do with our signs, remember we say one positive, one negative. It's going to be negative here and positive here. So if we try 3x times positive 2 is positive 6x. Negative 5 times x is negative 5x. So 6x minus 5x is positive 1x. And that's exactly what we were looking for. Okay, so I'm glad I was able to factor this. If you are not good at factoring, there are things you could do, to learn. You could find a video to help you learn how to factor. I wouldn't recommend just to search it online because factoring is a skill that you are going to need for pre-cal 2, for calculus, and if you're not taking those classes, I mean, I don't know what to tell you, but factoring is very important. So once you have your two factors, by the zero factor property, we take each factor and equal it to 0, and then we solve for the equation one at a time. So in this case, we will have x is equal to negative 2. And for the other one, we're going to have 3x is equal to positive 5. And then x will be equal to 5 over 3. 5 over 3, yes. And those are the zeros. And if you see, they match the graph that I had left there. So that is a way to find the zeros. So what will we do here to find the zeros? We're going to do the exact same thing. And here I'm just missing the part that will say the square root of 10 minus x squared. That is equal to g of x. Remember, functions could be called g or h or any other letter, almost any other letter, not only f. So the first step here says set g of x equal to 0. So that step was already done for us. It's right here. They replaced g of x with 0. Now, how could we undo a square root? So the inverse operation will be to square it. But whatever we do to one side, we have to do it to the other side. So we square the 0, which is kind of pointless because it will still be 0. Now, when we square the square root, we cancel the square root and we get 10 minus x squared. So now from here, what I'm going to do is take that negative x squared across the equal sign. And now it's positive. It has that invisible plus. And from here, what I'm going to do is take the square root on both sides. So you already know that here is going to cancel, so it will just be x. And on the other side, it's going to be the square root of 10, positive and negative. What does that mean? Well, that you have two solutions. One of them is with the positive square root of 10, and the other one will be the negative square root of 10. Remember, the negative is outside. And you can see those 2 points here. They are x-intercepts because they're real numbers. Square root of 10 comma 0. So here, these two are called the zeros. What's another word for those? Roots. What's another word? Solutions. Solutions of the equation, and you can see them here. They're touching the x-intercept. So the actual points here they're called x-intercepts. There we go. Okay, we have one more. Example 3. So here again, the first step says set h of t equal to 0. So I'm just going to write it here so you understand exactly what they mean. So now you can see that t is the independent variable instead of x. And this is very common to represent time. And then instead of y, they're using h of t to represent the output of the function. So again, very common. So it says set h of t equal to 0. Here it will be like the same equation. I'm just going to write it so you don't get confused. There we go. Now, what I'm going to do is take now I replace the h of t with 0 because I'm trying to find the solution to the equation, or the zeros or the roots. And the best thing for me to do will be to take the t plus 5, which is in the denominator, is dividing the other stuff on top of the fraction. So if I take that whole thing across the equal sign, it's going to perform the inverse operation. And that inverse operation is multiplication, you know very well. So if you multiply 0 times something, it's just going to be equal to 0. So it's kind of nice to have that. Now we still have to solve for t. But before that, we're going to add 3 to each side, or like, you know how I like to say it, we take the negative 3 across. And so from subtracting, it's going to go to adding, so it will be positive 3. Now from here, we're going to divide each side by 2, or like I like to say it, take that across, it goes from multiplying to dividing. So t is equal to 3 over 2. What does that mean? That this little number here is going to be my 0, my solution, and my root of the function. So you could see it because 3/2 is a real number. We could actually see it as an x-intercept right here, and those are the coordinates of the x-intercept. Remember, x-intercept because it is on the x-axis, and by default the y must be 0, and that's also why we call them zeros of the function. Okay, the next concept is the increasing, decreasing functions. So we're always going to read the graphs from left to right. Always, always, always. And if we look at the example here, we could see how from x negative 2, actually I'm going to use a different color, from x equals negative 2 to x is equal to 0. I'm going to draw it here, 0. The graph is decreasing. Okay, and then from 0, from x equals 0, so the first one was from negative 2 to 0. The next one is from 0 to 2 for x. The graph is constant. It's horizontal. It's not decreasing nor increasing. And then finally, for x equals 2 to x equals 4, the graph is actually increasing. So we always take the smaller number connected to the bigger number. Same thing, smaller number connected to the bigger number, and then smaller to bigger. Now, the numbers that repeat, such as, let's see, we have x equals 0 here, but we also have it here. And then we also have x equals 2 here, but we also have it here. So when we write down our three intervals, we will use parentheses, because at that particular x value, the one that repeats, is not increasing nor decreasing. It's just where it changes. When you take calculus, you will learn how to find those points. They're called critical points. They're very important. Now, because we see a closed circle here, I'm going to go ahead and use bracket. But if we didn't have that closed circle, then I will just use parentheses. So in this case, it will be decreasing from -2 to 0. We use parentheses because we're going to use the 0 again over here. And that will be for constant. So from 0 to 2, also parentheses because we're going to use 2 over here. And that will be for increasing. And that will go to x equals 4. So I want you to please make a note that you always give your answer in x intervals. Not as the coordinates of a point. And I know that's going to happen. It always happens. I don't want you to tell me this point being -2, 4. That will be wrong. You have to just tell me the answer in x intervals, just like what we did here for all three. Okay, so here's a formal definition of increasing, decreasing functions, and also constant. So a function will be constant. Let's start with it. If we have for any x1 and x2 that are different, and the y values are equal. So the inputs are different. That's why they're labeled with a different subscript. But the outputs are equal. This is saying that the same as saying that the y values, like y sub 1, is equal to y sub 2. So that happens also graphically when you have a constant function, which is y equals to a number. Let's call it 3, for example. So that will be constant. The function is constant. Now, the function will be increasing if we have x sub 1 less than x sub 2. So in the number line, x sub 1 will be smaller, so it will be to the left. And for example, if the y values that correspond to it, they happen to be the y value that corresponds to x sub 1 is, let's say, down here, and the other one is going to be bigger, like let's say here. So that would represent increasing. And then finally, for decreasing, it will be the opposite. We locate the x values the same way. X sub 1 is going to be in front of, it will be smaller than x sub 2. But now if we look at the y values, we could have f of x sub 1 up here, and then f of x sub 2 could be like down here. Like f of x sub 1 will be bigger, so that will be a behavior of decreasing, sorry. So decreasing and increasing and constant. We're going to use the graphs to describe the increasing, decreasing, or constant behavior of each function. So for the first graph, the part A, we have the equation, and I know that it might be a little debatable if it's like decreasing somewhere around here, but I can tell you for sure that it is increasing the whole way. So it does not have, remember how the previous graph that we work with had those points, and so that's why we were using the brackets to include those numbers, because that's where it was stopping or starting to decrease, or stopping to increase. However, the graph that we have here does not have those points. So we're going to assume that it keeps going, that it has those arrows. Also, we have the equation, so I can tell you for sure that the domain is all real numbers. So we could say from negative infinity to positive infinity. So the increasing part is going to be from negative infinity to positive infinity, just like the domain. Now, next graph, we're going to also assume that it keeps going, also because we have the equation there. It is a cubic function, which we're going to study more in chapter 2, or a polynomial of third degree. So in this case, we could see two behaviors. First is increasing, and we're going to say that, remember that you must give your answer in x intervals. So x intervals. So we will start from negative, well, I'm going to write increasing first. Increasing is going to be from negative infinity, and then we're going to stop at x equals 1, negative 1. And it's also increasing again here from x equals 1 to x equals infinity. So we're going to say from 1 to infinity. Okay, now for decreasing, it's going to be from what I'm going to highlight in blue. And again, we have to use those x values. So it's going to be from negative 1 to positive 1. So decreasing from negative 1 to positive 1. In this case, we use parentheses with all of them because those values that are repeating, such as negative 1, 1, negative 1, 1, those are representing the x values of the critical point. So it's not increasing nor decreasing, it's just where it changes. Again, you will learn more about that in calculus. Okay, and we have one last graph. Again, we don't have that like starting and ending point, so we're going to assume that we're going to infinity and coming from negative infinity. So we're going to have first, it's pretty easy to notice this one, we're increasing. And so increasing is going to be from negative infinity to the x value that you see here, 0. Remember, always give your answer in x intervals. then it becomes constant. And it becomes constant from x equals 0 to x equals 2. And then it starts decreasing from x equals 2 to negative infinity. And remember, they are x intervals. We don't want the coordinates of the points when we answer questions about increasing or decreasing. We only want the x intervals. Okay, based on increasing and decreasing, remember I told you those points where it changes in calculus, we call them critical points. For this class, and in fact, you will use that language in calculus too, we call them the relative minimum or relative maximum. And the reason we use the word relative is because we are working in a close interval, meaning that we're not considering the whole function from negative infinity to positive infinity, but we are just taking like one part of it. So for example, this is one interval, and then here this will be another interval, and then we have another interval here, and then we have another interval over here. Okay, and we have to do that because this function could well just keep going like that. And so, of course, there will always be a higher point than those that we're calling relative maxima. So that's why we cannot just say the maximum or the minimum. We have to use the word relative. Now, in singular, we'll say minimum or maximum. In plural, we will use maxima or minima. But remember, they're all related to the interval for which they are, they belong to the on the graph. So just like the description says, it's gonna be something that it looks lower than the points around it. We could also call it, what do they call it? Like a valley. And then the other ones, the maxima will be like a hill, like that. Okay, so what that means is that for that close interval that we were discussing, we have one x value for which it will be the minimum. If you notice, it will be the smallest of all the other x values. So that will be the minimum. And again, for a close interval, we will have an x value. In this case, it happens at x equals a, but the actual maximum is the y value, always. That will be the greatest y value of all. And the minimum also, we use the y value. And the x value is just simply where it happens. That a represents a real number. Okay. So if you are given questions of, let's say let's put some numbers here. Let's say that's a 1 and this is 2. And the question is, find the relative minimum of the function for the x interval from 0 to 2. So, of course, you will be focused on this point. And so the relative minimum at that point will be y equals 2. Or if the answer already has the y printed and the equal sign in just a box, then you just enter 2. Or it could be f of x equals 2. And if it says where does it occur, then it will occur at the x value equal 1. Okay, next concept, rate of change, average rate of change. And I know I mentioned this when we started covering the slope of a line. And just to remind you that any function like the one we see here, it does have a slope, and it will be the average rate of change between any 2 points. So in this case, it does look like a secant line because it's cutting the graph or intersecting the graph at 2 points. And those 2 points are going to be x sub 1, f of x sub 1. Instead of calling it x sub 1, y sub 1, we call it that. And then the other point, x sub 2, f of x sub 2, is representing x sub 1, not 1, but 2, x sub 2, y sub 2. There we go. Okay, so going back to the formula that we had for the slope of a line, that used to be the formula, not x, oh my gosh, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So here we're using the exact same thing, but instead of calling it y sub 2, we call it f of x sub 2, which is the same thing. It's just the output when x is equal to x sub 2. And then for y sub 1, we are replacing that with f of x sub 1. And that will be the same formula as the slope. And remember that this is telling us the difference here. The numerator on top is telling us the change in y. So delta y. Delta means change. And we use the triangle symbol. And then change in y, that will be delta. Oh, I say change in y, sorry. Change in x, that will be delta x. And of course, you already know that those are calculated by finding the difference in y and dividing that by the difference in x. What else could we say about this? That it could be called the rise over run. And so that is our average rate of change from 2 points, from two x values, x sub 1 and x sub 2. Okay, so we're going to find the average rate of change. So it's like we're finding the slope of a function that is not linear, and that's perfectly fine. So we have 2 points, or well, we have two x values. One of those is x sub 1. So if we have x sub 1 is equal to negative 2, we need to identify what is the output for that x sub 1. In other words, what is the y value when x sub 1 is negative 2? So for that, we look at the graph, and we have this point here. And we see that if the x value is negative 2, the y value is also negative 2. So from here, it's like we have the point negative 2, comma, negative 2. This is x sub 1, and this is f of x sub 1. Now, the other x value is negative 1. So we have that when x sub 2 is equal to negative 1, what is the value for that x value. So what is the function value, the output for x equals -1? Remember, this is the label, and this is the actual x equals -1. So if we look at the graph, find the x value of -1. It's this point here, and we could see that the output, or the y value in this case, is +2. So we have the point -1, comma 2. This is x sub 2, and this is y sub 2. So now we're going to find the slope by using that formula, f of x sub 2. And yes, that's what I should call this one here. Minus f of x sub 1 divided by x sub 2 minus x sub 1. So f of x sub 2, we have it here is a 2. And then we have a minus. And then f of x sub 1, we have it up here. It's a -2. Then we divide by the x sub 2 number, which is -2. Oh, sorry. That should have been here. X sub 2, remember. So -1 minus the value for x sub 1 right here. So that's -2 as well. So you see how the negatives that I have here are part of the formula. The other negatives, they're inside the parentheses because they're representing the y sub 1 and the x sub 1 values, which are both negative. So I do that so that I don't have any confusion and I don't forget to simplify that. So two negatives, I get a positive because they're multiplying. And then on the bottom I will have -1 plus 2. So this is going to equal 4/1. So the slope is 4/1, or just simply 4. And you could see how the slope happens to be positive. So the reason the slope is positive is because the graph is increasing, which was one of the questions that we answered previously. Now for the next part of the example, we're going to find same equation, but now we're going to find the from another set of x values. So we're having x sub 1 is equal to 0. We want to find the y value. And then for x sub 2, we have is equal to 1. So we want to find the y value that goes there. Now, we're going to pretend that we don't have the equation, but we only have the graph. I'm sorry, the other way. Not the equation, not the graph, but we only have the equation. So for that, we're going to have to substitute. So what we're finding here is f of x sub 1, which is equal to f of 0. So if I take the equation that you see here, and for every x that you see, I'm going to substitute it with a 0. So this is going to turn into 0 to the third power minus 3 times 0. So this is going to equal to 0 minus 0, which is 0. So what this means is that f of x sub 1 is 0. So that goes here. Now let's do the same with the other x values. So we need f of x sub 2, which is going to be f of 1. And for that, now we're going to substitute the 1 to the third power minus 3 times 1. So this will equal to 1 minus 3, which is equal to negative 2. So that goes here, negative 2. So this is y sub 1, or I should call it f of x sub 1. And this is f of x sub 2. All right. So that's how you will do it if you didn't have the graph and only the equation. Now let's go ahead and put them into our formula to find the average rate of change. So f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. So we will get f of x sub 2, that will be negative 2. That is here. And then minus f of x sub 1, which is 0. And then we need x sub 2, which is 1. And then minus x sub 1, which is 0. So now we get negative 2 minus 0 is negative 2. And then 1 minus 0 is 1. So the slope in this case is negative 2. And you could see that it is negative. So the negative slope is happening here. And you could see that at that point of the graph, it is decreasing. The graph is decreasing in that interval. And so that is why the slope is negative. So negative slope means the graph is decreasing between those 2 points that we chose. What 2 points? This one and this one. How did we get those points? From the x values here. How did we get the y values or the outputs? By substituting the x values into the equation. The equation, we took it from here. Okay, so let's move on to the last topic of this section, which is even and odd functions. Now, I don't want you to think about odd and even numbers, just functions. Okay, so we already covered a little bit of symmetry, and we went over symmetry across the y-axis. And just so you know, those functions are called odd functions. And then we also, I'm sorry, no. Those are even functions when they're symmetric with respect to the y-axis. Even functions. And then they are odd when they are symmetric with respect to the origin. So the way we could check by looking at them and seeing if you get the same if you replace x with negative x or y with negative y or both x and y with the opposites. But there's another way to check it algebraically as well, and that will imply replacing the x value, as you can see here, replacing x with a negative x. And so if you do that, the idea is that if you get like the identical function after replacing the x with a negative x, then your function will be even and therefore symmetric with respect to the y-axis. Now, if you do the same replacement of the positive x, as you can see here, positive x with negative x, and then now what happens is that you get the complete opposite. And I say the complete opposite because instead of having the original function, we have a big minus in front of it. So you get the opposite of f of x, the original function. So if that happens, then you say the function is odd. So if you get the same, the function is even. And if you get the opposite, then the function is odd. Now, what if you get something in between? Well, then the function will be neither. And that could also happen. So if you get the same after replacing the x with negative x, the function's even. If you get the opposite, the function is odd. So let's do the example here. So we're going to check if this function is odd. Well, actually the answer is there already, but let's see. We're just going to do the replacement. So we're going to replace x with negative x, okay? So we're finding g of negative x. Remember, this is the original equation, okay? So if we replace, we're going to have negative x to the third power. So we're substituting that. And then minus, we have another x, so negative x. So let's see what happens here. So g of negative x is going to be equal to, this part here is going to be negative x cubed. Because if you have three negative numbers or variables multiplying each other, from the first two you get positive x, but then you multiply by another negative x, so then it's going to be negative x to the third power. So that's why it's negative x cubed. And here we have a double negative, so that will be positive x. Now, if we compare this equation to our original here, you could see that we went from positive x cubed to negative x cubed. And we went from negative x to positive x. So what it means here is that we got the complete opposite of g of x. So what we have is that after replacing x with negative x, we got the opposite of the original function. And so therefore the function is odd. And remember, functions that are odd are symmetric with respect to the origin. Okay, next example. Now we're going to check the function that we have here. That's the original equation. So just like it says here, we're going to substitute x with negative x. So we're going to have negative x in parentheses and then square it and then a plus 1. So by simplifying that, the negative x squared is like negative x times negative x. So negative times a negative is positive, so positive x squared. So that is what I'm going to say here. Positive x squared plus 1. Now I need to compare what I got with the original function. And you can see clearly that they are identical. H of negative x is equal to h of x. They're exactly the same. So because of that, the function is even. and therefore symmetric with respect to the y-axis. Now, we are not going to check for symmetry across the x-axis because we already moved on from relations to functions. And so if it was something symmetric with respect to the x-axis, that means it wouldn't pass the vertical line test because the x values will be repeating and those will not even be functions. So there's no such thing as even odd in symmetry across the x-axis. Okay, so right here on the last slide is just the graphs of the two examples that we did. So you could see that we found the cubic function to be odd, and that odd function symmetry with respect to the origin, we already wrote that down. And you can see those points there. Both x and y change to their opposites. And then the one with that was an even function, that was symmetric with the y-axis here. So you could see how the x, positive x, goes to the negative x, but we get the same y value. In other words, f of x is the same as f of negative x. They're the same. So that's why we say that the function is even. In the other case, we have that here f of negative x is not equal to f of positive x, but is the complete opposite, right? We went from negative to positive, so we call it the opposite. And so that's why the function is odd and therefore symmetric to the origin. So this is the end of the video.